all organisms have a need for acquiring and using energy. That is one of the unifying characteristics of life you've learned about since you began the study of biology in Bio 211. So energy is going to be something that animals are going to be acquiring through the consumption of food. And one of the things that would make animals unique is that in the way they obtain food and the way they consume it is going to be by ingesting it. Ingesting it means that they have to use some kind of a mouth structure to take in food, and that is going to be later digested. This is going to be different from other organisms like fungi, which, like animals, are also heterotrophs. Heterotroph means that they have to feed on something else or eat something else in order to acquire energy. Well, the deal with fungi is that they have to digest the food outside through the secretion of enzymes, and then the cells of the fungus will begin the process of absorbing pre-digested food molecules. That is not the case with animals. Animals are going to ingest, not absorb, but ingest food through some type of a mouth cavity. And later we've been exploring animals that are so advanced in terms of the mouth. They even have jaws for making it even easier to cut the food into smaller pieces before they can ingest it. So the main resource animals are trying to obtain from the food they consume is going to be energy. Well, in addition to energy, there is going to be other nutrients, including vitamins, minerals, essential amino acids, essential fatty acids, and other materials that animals can use for building body structures or to provide the essential ingredients cells need as part of their metabolism. So as we explore more about animal form and function, we have to look at this direct relationship that exists between animals and the need that they have for energy and how they go about absorbing it. The larger the body of the animal, usually the greater the amount of food they have to consume and the greater the amount of energy they will have to use. So in biology, we use this word called bioenergetics. And this is going to be to describe what bio, that is going to be life, and energetics, the budgets animals are going to have in order to provide energy that is necessary for every activity of the animal. Nothing can be neglected. And in bioenergetics, what we're trying to precisely establish is how much food an animal must consume in relationship to the size of the body of the animal, the levels of activity they perform, and also the type of environment where they live. Those are going to be the three main constraints for deciding how much food an animal will consume: body size, levels of activity, and the type of environment where they live. So one of the things that we can measure about an animal, and we can say, well, this is how much energy an animal will need, is if we can measure the metabolic rate. The metabolic rate is going to be the amount of energy that is used per unit of time. And so I provided here for you this simple but effective definition for what metabolic rate is. Now, there are two ways you can make this measurement, and one of those is going to be by looking at how much heat an animal is releasing. You can also say losing. The amount of heat released is going to be directly proportional, meaning that as the animal is losing more heat, that is going to be evidence of more energy that the animal has used. Because remember the second law of thermodynamics: with every energy transformation, there's going to be an increase in disorder, and this disorder can be measured by looking at the amount of heat that is released following an energy transformation or chemical reaction. So heat loss. The greater the loss means the animal is using more energy. Then you can also look at the amount of oxygen that is being used up over a period of time by an animal, and also the amount of carbon dioxide that is being released. So as we know, oxygen is going to be one of those necessary components for aerobic respiration. With oxygen at the end of an electron transport chain, electrons can be picked up, hydrogen ions are also taken, water is formed as a byproduct, but we need the oxygen to be able to pick up the electrons at the end of the electron transfer chain, so more ATP can be made. And carbon dioxide, as we know, also is going to be one of the byproducts that are released as a sugar molecule or other fuel molecules that are used in the process of making ATP. So the molecules are being broken down, bits and portions of the molecule are broken off and released eventually as CO2, carbon dioxide. And so here in this illustration that I have in this slide, you can see what happens in terms of the organic molecules that are in food. It is going to be from organic molecules such as carbohydrates, lipids, and even proteins that animals are going to be able to obtain energy. Those molecules are going to be digested. There's going to be some absorption. In the process of digesting, some heat energy is going to be released. There's going to be some energy that is never retained by the animal, and it's going to be part of the waste that the animal is going to be releasing, excreting. There are going to be nutrient molecules in body cells. Now we're talking about the carbohydrates that were retained from food, the lipids that were retained and absorbed, and those are going to be a source for cellular respiration. The simple work that cellular respiration would do will end up releasing additional heat, but a lot of energy is going to also be retained in the form of ATP. This will power cellular work. When cells work, they release more heat. Sometimes it's not the work cells are doing, but the molecules and the cells and the tissues they are building. That's what we call by biosynthesis. That will also end up releasing additional heat. And sometimes a few of those molecules will remain and become part of the body of the animal as the animal continues to grow and get bigger. Those will remain at least temporarily in the animal body. So that's the concept we're trying to explore in this short video. Bioenergetics. Animals are going to need to acquire and use energy, and that is going to be something that depends on animal size, activity, and environment. So one of the specific measurements we can obtain for how much energy an animal is using over a period of time is going to be if we can establish the basal metabolic rate, or BMR. The basal metabolic rate is how much energy an endotherm. Now remember that endotherms will be animals like mammals in general, birds in general. We can also count ourselves in this list of endothermic organisms. We are going to have internal organs and strategies for the release of heat if necessary, or retaining heat so we don't lose it right away. So that's an endotherm, endo, inside, therm, heat, internal sources of heat. So we can measure how much energy an endotherm is using at a comfortable temperature during resting conditions. Then we end up with this basal metabolic rate. And here's what we have learned about basal metabolic rates. Is, as I said before, it's going to be directly proportional to the size of the animal. And there's even an equation we can use where M is going to be the mass in grams, and then it's going to be an exponential type of a relationship, whereas body mass increases, so will the amount of energy the animal will need and will be using over a period of time. And so you can see that here small animals, small mammals like shrew, mouse, a harvest mouse, all the way as high as an elephant. You can say, well, that is no brainer, right? The larger the body of the animal, the greater the need is going to exist for supplying all of the conditions cells need, for supplying all of the nutrients and oxygen and water that these cells are going to be needing. All of that is work, and all of it requires energy. Smaller animals are going to have higher metabolic rates per gram. And this is interesting because if you look at this graph now, here once again we have the basal metabolic rate, and what you are going to see is that per gram of mass in tissue, there's going to be a greater energy expenditure the smaller the animal is. Now, what is different between this graph and the previous graph, I want you to be clear about that, is that here we're just simply plotting the entire body mass. So an elephant would have a greater body mass far greater than something like a squirrel. So here we're plotting body mass. But on this next slide, we're actually looking at energy consumption per gram of the animal. And so then we're plotting that in relationship to mass, and we can see that as the size of an animal decreases, body mass of the animal decreases, the amount of energy needed per gram of tissue is going to be increasing. And then when you look at larger animals like an elephant, per gram of tissue, the amount of energy they're going to be using is going to be less. And so you may be asking, why is this the case? And there's a couple of explanations that come to mind. One of those is going to be that the smaller body of a small animal like a mouse is going to require greater amounts of oxygen, greater amounts of water. There's going to be a greater development of capillaries for the delivery of blood, more nerve cell activity for every one of the cells. Just about every cell is going to have their own supply of blood, of their own connection to the brain by means of neurons. And so that makes the running of a small body very expensive. And so that is going to be one of those. And I listed some of those conditions here on this slide. Higher oxygen delivery, higher heart rates, breathing rates, greater blood volume, that they're going to be in relationship to the larger body. A smaller body is going to be moving a greater blood volume, so the heart has to work even harder. Added to this, you can compound the relationship between object size and surface area. And so this is, again, a concept we learn in Bio 211, where you learn that a smaller cell or a smaller object is going to have greater surface area in relationship to the internal volume. And this is why cells are small, because a smaller size means that there's going to be a greater surface area, greater membrane area in proportion to the internal volume. And so what happens is that in the case of a smaller body, that proportionally larger surface area is going to make it more likely for heat to be escaping at a higher rate per unit of surface. And so when you look at something like a larger animal, so the larger animal, of course, they're going to have more skin overall, but when you divide the surface of the skin by the trillions and trillions of cells we have inside, there's going to be a smaller surface area in proportion to the volume and the number of cells inside of the animal. Consequently, a larger body is better able to retain internal heat. And so that's going to make it cheaper, more effective to run a larger body if one considers the energy that must be used sometimes just to maintain the steady internal environment. And so that's an interesting relationship that happens here. Obviously, there is going to be a greater need for energy in endotherms just because of that luxury, if you want to call it that way, of maintaining a body and releasing heat when necessary to maintain internal constancy, to maintain homeostasis. Whereas an ectotherm, they don't have to be generating heat from inside. They can rely on external sources of heat. And so that is going to be a benefit to them in terms of not needing as high value for energy consumption. Energy budgets are also going to exist for animals, and one of the things we can appreciate from looking at this graph is that how animals allocate energy is going to vary. It's going to be depending on the organism, on their activities, and also the environment where they live. So if you look, for example, at the annual energy expenditure for a person, you will see that our basal metabolic rate is going to be using a lot of that energy. Ideally, our basal metabolic rate, which in the case of men happens to be around 1,600 to 1,800 kilocalories. In the case of women, it's going to be about 1,400 to 1,600 calories. If we could double that, we could ensure that we can maintain a healthy body mass and good health overall. And so what we can see is that sometimes in developed countries, like what we have in the United States, our entire metabolic rate daily metabolic rate is going to be about just half, 50%, I'm sorry, higher than the base of metabolic rate. And that just means we have a comfortable life. We don't have to work too hard sometimes on most days. And looking at this graph again, you can see here the basal metabolic rate. The standard metabolic rate would be for animals that are ectotherms. So here you see that there's going to be a proportion of that energy budget annually that goes into reproduction. Another portion is going to be for thermoregulation, growth, and activity. It would be nice if our activity expenditure would increase, especially in this society where we live now. That is going to be changing. When you look at an animal like a penguin, they're going to have a greater budget for activity. And that's because this is going to be one of those animals that lives in a cold environment. And for thermal regulation, sometimes increased activity, going in the water and swimming and moving is going to be necessary for increasing the amount of heat that is generated. In addition to that, there's going to be a certain amount of energy that will go into reproduction. And the thermal regulation is not necessarily that much greater than what we do, but a lot of the heat these animals need will come from the activity. Now, to take a look at a mouse, a deer mouse from a temperate region in North America, and you will see here that activity is not going to be as high. These animals are going to have basal metabolic rate that is going to be lower in proportion to the other two examples that we have. Greater amounts of energy will be used here for the purpose of reproduction. And when we talk about reproduction, you will see why. For these animals, their success for the species is going to be in the numbers of offspring that they produce, because many of the young and the adults are victims to predators. You know, they are consumed, they're eaten. They have to produce greater numbers of offspring, and so there's going to be a greater investment in reproduction. And in terms of thermal regulation, well, we learned already that a smaller body is going to have a greater need for generating heat, because more heat is going to be lost through the proportionally larger surface area they have in comparison to the internal volume and the number of cells that they possess. And so how can animals conserve energy? There are going to be strategies. For example, sometimes animals don't want to be trying to keep an internal body that is warm when outside is just going to be right out cold. And so many animals are going to engage in a daily pattern of torpor. Torpor, or daily torpor, is going to be a physiological strategy where an animal can lower its metabolism and energy consumption and use, allowing their own body temperature to drop, their own heart rate is going to drop, and metabolic activity in general is going to be lower. Now, this happens on a daily basis. Many birds, reptiles can do this, mammals can also do this during the nighttime. They're going to allow their body temperature to go down. So at nighttime, they're going to be more of a poikilothermic type of an organism. And what happens when the sun rises again, just a little bit of activity, just positioning their bodies in a place where they can absorb some radiation, that is going to allow them to increase their metabolic rate and resume their activities. And so, torpor. Here you see an animal. This is a bird that finds on a nightly basis a depression on the ground. This is a nightjar. It's the name of this bird. And sometimes hikers will stumble upon a depression on the ground. They see the bird. They see it's like it's not moving. They may think it's dead, pick it up. And if they do that and they hold it, after a couple of minutes of holding it, just the heat the human hand is transferring to the bird would increase the metabolism, and the bird is going to start fluttering and moving around. Other people have made the mistakes of maybe they're in the desert and they come across a rattlesnake, like a sidewinder, that appears dead. It's just laying there. It's not moving. They'll pick it up. But soon they may have a good scare when the snake begins to move. And so it's not that it's dead. It's just that they have allowed the body to enter this daily torpor. How is that different from hibernation? hibernation is going to be like a more extended state of torpor. It's going to extend for months, weeks, but for sure months. And in hibernation is a prolonged state of sleep where heart rate drops, temperature drops. In some animals, like ground squirrels, their temperature can even drop almost to freezing point. And so the heart is going to beat maybe only twice per minute. The circulation is going to be greatly decreased. Animals that are hibernating, truly hibernating, sometimes get a little bit active just to change their position, just to, again, get some oxygen moving into the bodies, but then fall asleep for a couple of weeks. The true sign of an animal that is in real hibernation is going to be that if you pick it up, it is not going to move. Here we see, in this example, there was some road construction somewhere in North America. I'm not really sure where the photo was taken. The machine is cutting through the ground to make a road, and they came across this chamber where a woodchuck is sleeping. Despite the noise, despite all of the activity, and even now exposure to the air, the woodchuck did not move. They can't. Even if they wanted to, they sense, okay, something is outside. They cannot just like jump and start running because their metabolic rate is so low, the body temperature is so low, heart rate is so low, and so they cannot react to that. Perhaps if we have time in class, or if somebody reminds me, we can have the conversation. So what about bears? Do bears truly hibernate? Can a bear be woken up from sleep and immediately get active to the point that it can attack a stranger? Well, the answer is yes. And so do bears truly hibernate? Maybe we'll have time to talk about that in class. Anyway, that is all that I have for this topic of animal principles of animal form and function. And I hope you find these videos useful as you continue reviewing and studying the concept for this chapter 4. Goodbye.